Hello everyone. Today's topic is about Danksharding, and let's get started. And uh, and what is Danksharding? Danksharding is a total new design of sharding. It's not to enhance like a cross-chart communication or to reduce slot time. It's a total new design of sharding. And before we start, some knowledge we need to know first. First is about the original design of sharding. In case of confusing, I use sharding 1.0 here, and you can see the diagram here. Basically, the original design is to separate current existing POW mentioned into three different layers, which is beacon chain, the consensus layer, and the structure, the data layer, and the execution layer. So I believe everyone know what beacon chain is. Validator just vote on this chain, and the shard chain is only data chain, so there's no EVA on top of it. So basically, it's only for data storage. And in their roadmap, in their original roadmap, they also separate into separate three phases. So beacon chain is phase 0, phase 1, and phase 2. And yeah, this is about sharding 1.0. And the challenges in sharding 1.0 is because we have many different shard chains, so validators need to be separated into different shard they call committee. So to avoid collusion or private attack, so validator need to rotate to different shard to validate different shard chain. So periodically, so there will be a synchronization overhead. That means when I'm in shard A, so after a period, I need to rotate to shard B, and that means I need to download all the data and transaction history from shard B. So that is synchronization overhead, and you need to do this over and over again. And the second and third is similar thing. It's about cross-shard communication, and I think everyone knows because we have different many shards. So if you have a transaction in shard A, and you need to access some states from shard B, so you need to wait you need to wait several slots to get a state because you need to wait the state finalized. So this was UX, and the last one is MEV. And because your data has been finalized in shard A, so everyone knows the state in shard A. So it's easier to MEV this kind of situation because transactions are in different shards. So those are changes in the original design shard 1.0. And the other thing is October 2020, Vitalik posted idea. It's called roll-up centric roadmap. So the background at that time is roll-ups. No matter roll-ups has been quite mature. ZK Sync has been online for a while, but only token transfer. And the optimistic rollup, no matter Optimism or Optitron, had the testnet already at that time. So it's quite mature for rollups. And the other reason is the execution layer, the phase 2 I mentioned earlier. They have some development issue. I don't know the detail, but yeah, they have the issue to develop that. So The idea of Vitalik is to try to replace the execution layer with rollups. That also means the layer 1 only become data layers because there is no execution layer. Execution layer goes to rollups. And yeah, so go back to our topic today. So what is Danksharding? Danksharding is proposed by Danksharding, who is a EF researcher, and proposed in the end of 2021. Basically, it designs a one large block design, which means there's no short chain anymore. There's one single chain, which is bigger chain to store the data. And the block size, you can imagine there will be 256x. There will be, data will be 256x compared to current block. So there will be a huge block. So you can see this diagram. So here is the block in this design. So it also includes the existing bigger block for consensus, and the data still be shorted into many shards. Now it's 256. So there will be a huge big block in this design. And you can imagine in this design, there will be very resource intensive, no matter computational or storage. You need a very very good computing power to process these transactions, and also you need to a larger storage to store this transaction because the block is so huge now. The other is network. So because the block is very big now, so the block synchronization is also an issue for this design. And then, and the more resource intensive, which also implies more centralized. So let's see how they solve these problems. So the first is data availability sampling. So what is data availability? I would say DA for data availability in this talk after. So it's quite simple. The definition is quite simple. You can download the data if you really need to. So let's take rollup as an example. Everyone knows rollups basically put their transaction data on chain, on layer 1 chain. So like optimistic rollup, if you found the operator do something bad, you can find your transaction history from layer 1 chain, and to submit fraud proof. So this is the idea of the DA. And another kind of So another kind of rollup called Validian is basically the same as rollup without submitting transactions on chain. So basically, if you go to a network which is if the network is Validian, which means you need to trust the operator inside the network. If they do anything bad or collusion, nothing you can do because they hold all the data. You cannot submit fraud proof or anything like that. So this is DA. If you have data availability, you are able to do you are able to prove something. Yeah. And then the first question is, how do you check data is available without really download it? It means if everyone check the DA through download all the data, it's apparently not scalable because the block size is so huge now. So you need to find a way to, for validators, not download all the data, but still can check the data is available. So the answer is sampling. So the idea is through sampling to check the DA. Let's take for example, you can split your data into 100 pieces. So let's say the whole network has 100 nodes. So if every node sample 10 pieces of data, so there will be 1,000 times sampling, which means there will be high probability that all the data is available, because ideally each piece of data will be sampled 10 times, ideally. But in practical, at least each piece of data will be sampled 2 or 3 times, but it's enough to check. So through the sampling, you only need to download like 10% or 5% of data, and then through the whole network do the same thing. So whole network can say that the data is available. And the next question is, what if only one piece of data is missed? That means you need to check 100% availability. And yeah, let's take an example here. Let's do a simple math. And the 0.99 here means you owned 99% of data. Just like I said, you only miss one piece. And the 10 here means every node sample 10 times and sample 10 pieces. So the result will be around 0.9, which means 90%. What does this mean? It means if you are a validator and you sample the data to you sample the data, and there will be 90% you will trust the data is available. And it also implies that the whole network, there will be 90% nodes believe the data is available. But this kind of situation is not acceptable, because you miss one pieces of data, which means you cannot reconstruct the data. So how do they fix this? They through erasure coding. So what is erasure coding? It's quite a common and mature tech, and it happens in our daily life, like network transfer, or like our hard drive, like RAID 0, RAID 1, I forgot which one. So basically the idea of erasure coding is you extend more data. Let's say you have 100 pieces, you extend one more 100 pieces. So you only need 50% plus one pieces. You can reconstruct the data. So that's erasure coding. So let's recap. So what we have now. So the idea is data is split into 100 pieces, and through erasure coding, we can get 200. And through sampling, we can say the data is available, but without really download the whole data. Yeah. So this is DA sampling. And the next question is, how do we know the data was erasure coded properly? And that means because we will extend one more pieces data. So how can we ensure the extended pieces are garbage or not? Maybe maybe block proposal just add some garbage into the extended data. So how can we ensure the data is erasure coded properly? We through commitment. And let's see some example. What is commitment? Hash function is a commitment, and merkle root is also a commitment. What is commitment? Let's take let's see an example. If we want to have a quiz in smart contract, so everyone can submit your answer to the contract, but if you really submit your answer to the contract, everyone can see your answers and copy your answer. So another way you can do is you hash your answer, submit to the contract. So basically the hash of your answer is the commitment, and wait for like time's up, and then you reveal your answer, and the contract can verify the hash of your answer is the same as the commitment you submit in earlier. Yeah, so that is the commitment. So the most common commitment we see is hash and the merkle root, but here they use polynomial commitment. The idea is the same, but it doesn't use merkle root. It uses polynomial. So I won't go to any detail here, but just let you know they use different commitment scheme here. And more precisely, they use KZG commitment. And you can see some article says Kate commitment is basically the same commitment scheme. And let's use merkle root as an example. So the purple ones, the four data are original data, and the green ones are extended, which is erasure coded. So you through the merkle root to create a merkle root. So after you download the data, you can make the merkle root to see if the data you download is correct. So this is a commitment to ensure the data is erasure coded properly. And the next question is, because our block data is very, very huge now, so create a commitment still needs a huge computing power. And why I say here to verifiers, because in this design, block proposal, how do I explain this? Because we want more verifiers, which is validators. So more validators means that more people validate that transaction or that block state. So it's safer if we have more validators in the network. So lower the hardware requirement here is very important for decentralized that. So yeah, this is the problem we have. So how do they fix this? They threw two-dimensional commitment scheme, which means you can see the diagram here, and the purple blue one, this one is original data, and the green ones are extended through erasure coding. So the idea is you can see there are 256 commitments, which means every shard has its own commitment. And that will be much easier for verifier to create a commitment because the data size is much smaller. And here is the erasure coded the commitment erasure coded commitment. So yeah, this idea to in the original we have big commitment and two-dimensional commitment scheme split the commitment into many small commitment. So that's the idea to reduce the hardware requirement for validators, verifiers. So the design now is every validator sample two rows and two columns from the block proposal. Yeah, and if the whole network have enough validators, we can make sure the data is available, as mentioned earlier. And yeah, but for block proposal, still need a huge computing power because you need to generate so many commitments. And also because the data size, the block size is so huge, means there will be like a 256x transaction number of transaction compared to now. So they propose the proposer builder separation. The idea is to separate the text into different roles. So first is builder. Builder is to collect transactions and reorder and extract NEV as much as possible, and then bid for proposer and to select the block. And the proposer is easy, just propose the block. Basically, proposer choose the highest bid and propose. So proposer can get the bid, yeah, the money from the bid. So this is the idea. And then but this kind of you may find that is quite similar to what we have now. That FlashBots have exactly the same mechanism. They have searcher relayer to do NEV extraction and then create a bundle, something, a block, and propose to miner and miner to propose the block. So that is basically the same as the FlashBots. And this kind of mechanism, if you do this, but the biggest difference is FlashBot is another application. If you don't want to use, you still can submit your transaction through the old existing way. Yeah, but this is in protocol. This design is in protocol, so there will be some challenges or issues for this kind of design protocol. So the first issue we met will be if builder build a block and submit to proposal, there will be two issues. One is the whole network will be many builder doing that. So and the block size is huge now, so there will be some network issue because there are big block transfer through the network. There's network issue. The second is if because the builder submit the whole content of the block body. So if I was a proposer, I can easily copy their block data and propose, and I don't need to pay money to builders. So they proposed the 2-slot PBS. So the idea is after builder create the block, they only submit the header of the block to proposer. Builder only submit header to proposer. Once the proposer accept the builder, and then builder submit the block body, the content of transactions to the whole network. So there will be 2 phases. And this kind of design will take 2 slots. And the slot time now is 12 seconds, and which means this kind of design will take 24 seconds to for validator to attestate your transaction. So they also propose that reduce the slot time to 8 seconds. So there will be 16 seconds for this kind of scenario. And as I mentioned earlier, this is in protocol design. So which means if I was the builder, I don't like you, I can reject your transaction. And that is called censorship attack. So how do they avoid to prevent from this kind of situation? They propose an idea called censorship resistant list, which means if you are a proposer, you create a list, CR list, and the list contain a list of transactions. And the builder need to include all the transactions in the list, and then do the same thing, propose block header and the propose content as mentioned earlier. So the difference is there's a list. Builder need to follow the rule and include all the transactions inside the list. That's the idea. But there's a flaw in this kind of design because proposer can submit an empty list. So basically, you will back to the same thing. So and this kind of design, proposer builder design, PBS design is still is still under discussion. The detail haven't decided yet, and that's PBS. And let's have a summary here. And through Danksharding, and there's no more shard chains, so which means there's no cross-shard commutation anymore. We can have better UX. And the higher security means because all the validators validate one single block, you don't need to be separated into different committees. So more people can vote, so there will be higher security. And the lower hardware demand for validators because the 2D commitment scheme. And as I mentioned, lower hardware demand is more decentralized. And yeah, here Vitalik posts an article called NGAN. So here's the idea of NGAN. So all rows lead to NGAN of centralized block producer and decentralized trustless block validator. So yeah, as you can see, the block producer still need very huge power because it need to handle such huge amount of transactions. So it still need very huge computing power. But we can, through the design, to decentralize the validator, so we can get a balance between these two. If any block producer doing something bad, we have huge validator set to verify and say no, it's not acceptable, something like that. And this is all about Danksharding. Okay, and then next let's talk about proto Danksharding. Oh, this post is in Mandarin. Yeah, proto Danksharding is also EIP 4A44. And what is proto Danksharding? Basically it introduced a new transaction format which can carry blob data, and the blob data is much more. You can carry more data size in blob transaction, and the blob will be deleted after 30 or 6 days. It's not finalized, and the blob data cannot be accessed by contract. So the idea is, let's see. So yeah, the first question is why not just reduce gas cost? Like EIP 44AA is different from proto Danksharding is 4A44. So through the blob data, you can carry more data but with lower gas. This is the idea of proto Danksharding. So let's do a simple math here, and we can see the current state. So we have 30 million gas limit. There's a cap for the current limit now. So 16 here is every single non-zero code data need to consume 16 gas. So we can get, if the whole block hit the cap, so the whole block will be around 1.8 megabyte, the data size. And we can see the proto Danksharding, and we see the spec here. Block size is 4K multiplied by 32 bytes, and every block can have 16 blocks. So the worst case, there will be 2 megabytes for each block. If the whole block carry 4 blocks, there will be 2 megabytes. And let's see for AA, which is reduced gas cost to 3. And so we can see the worst case scenario, 30 million divided by 3. The block size will be 10 megabytes. So that's much worse than we have now. So it's not a good idea to just reduce the gas cost, because in worst case scenario, your block will be your data size will be very huge. And then, yeah, the conclusion. So through the rollup-centric roadmap posted by Vitalik, layer 1 now becomes a DA layer only, so only for data storage. And through the proto Danksharding, it introduced block data, so you can have much more data in a transaction in a block, but the data will be deleted after a period of time. Now it's 30 or 60 days. And then through DA sampling, through the sampling, you don't need to really download whole the data. You need to download like 5 or 10% of data. So it's more like everyone becomes line nodes now. Only some nodes need to be full nodes, or any other validators becomes line nodes because they only need to carry part of data. So I think that's it for today. And here's some reference. The first one is really good ones, and written by Delphi Digital, but it's a very long article. And here the one is explain what is data availability, and it's a short thread, so very encouraged to understand what is data availability through this article. Yeah, I think that's it for today. Thanks everyone.